Look around you. At this very moment, you are likely experiencing a profound illusion. Perhaps you see a mountain, an ancient and steadfast monument to permanence, or a sleeping child, the very picture of serene tranquility. Maybe it is just the book in your hands, or the chair you are resting upon, seemingly locked in a state of perfect, unwavering stillness. This perception, this feeling of absolute rest, is one of the most pervasive and deeply misleading deceptions our senses present to us. It is a comforting falsehood, a local fiction told against a backdrop of universal, relentless, and inescapable motion. For if we could magnify our senses, if we could see the world as it truly is, that stoic mountain would reveal itself as a slow-motion storm of activity. Its crystalline structures are a lattice of atoms, each one a buzzing hive, their electrons whipping around nuclei trillions of times per second. The entire landmass is being imperceptibly compressed and stretched by the gravitational caress of the moon, breathing with the tides of rock. Deep beneath its roots, tectonic plates groan, grinding against each other, pushing the peak millimeters higher each year in a battle against erosion. The tranquil child is a universe of its own, a symphony of unseen kinetics. Billions of cells perform their intricate duties. Molecules are assembled and disassembled. Electrical signals race along neural pathways at hundreds of miles per hour. The heart, a tireless engine, pumps blood through a vascular network that, if laid end to end, would encircle the planet twice over. Air, a turbulent fluid of nitrogen and oxygen, rushes into the lungs, its molecules ricocheting violently within the expanding chambers. There is no stillness here, only the exquisitely organized chaos of life. This is the first layer of the truth, that on the atomic and biological scales, stasis is a physical impossibility. But this is only the beginning. This planetary activity is itself nested within a cascade of grander movements, a series of cosmic dances where our world is but a single, fleeting participant. The very ground beneath our feet, the bedrock of our perceived stability, is a platform hurtling through the void on a journey of unimaginable scale and speed. So, we must ask the most fundamental question about our reality. Why? Why is perpetual motion the default state of everything? From the frantic trembling of a subatomic particle to the majestic sweep of a galaxy, what cosmic law dictates that nothing, absolutely nothing, can ever truly stand still? The answer is not a single statement, but a story that unfolds across every scale of existence, from the very first moment of creation to the predicted end of time itself. It is a story written in the language of gravity, relativity, and quantum uncertainty. And it begins with the spinning ground we so confidently call home. For millennia, humanity lived under the grandest of all illusions, that we were the stationary center of the universe. The sun, the moon, the planets, and the stars all seemed to revolve around us, performing a daily celestial ballet for our exclusive benefit. It was an intuitive, comforting, and deeply egocentric view of the cosmos. To suggest otherwise was not just a scientific error, it was heresy, an assault on philosophy, on religion, and on common sense itself. Yet, the truth is far more dynamic and far more humbling. Our planet is a colossal sphere of rock and iron, spinning on its axis like a top. At the equator, this rotation carries the surface along at over 1,000 miles per hour, a velocity faster than the speed of sound. We do not feel this incredible speed, because everything around us, the atmosphere, the oceans, the very continents, is moving along with us, carried by the planet's immense momentum. It's like being a passenger on a colossal, smoothly running jetliner. You only perceive the motion when you look out the window at a reference point, like the unmoving backdrop of the distant stars. This planetary pirouette is the great engine of our world. It sculpts our weather, creating the vast, swirling patterns of hurricanes and the steady march of trade winds through the Coriolis effect. It is the master clock that dictates the rhythm of day and night, the cycle of waking and slumber that governs nearly all life on Earth. The simple act of a rotating sphere transforms our experience of the sun's light from a constant, unyielding glare into a life-giving, dynamic pulse. But this rotation is merely our most intimate, local motion. As Earth spins, it is simultaneously engaged in a much larger, faster journey. It is hurtling through space in a vast, near-circular path around our star, the Sunday. To complete one full orbit, 1 year, our planet travels nearly 600 million miles. This equates to a staggering orbital velocity of 67,000 miles per hour. That is over 30 times faster than a speeding rifle bullet. Every hour, we travel a distance equivalent to crossing the United States twice over. Every single day, we journey 1.5 million miles along our orbital track. We are held in this cosmic embrace by the invisible tether of the sun's gravity. The 16th century astronomer Johannes Kepler was the first to mathematically describe this elegant ellipse, but it was Isaac Newton who, a century later, explained the physics. He imagined firing a cannon from a very tall mountain. A small amount of gunpowder would make the cannonball fall back to Earth quickly. More gunpowder, and it would travel further before landing. But, Newton reasoned, if you could give it just enough velocity, its forward momentum would perfectly balance the downward pull of gravity. The cannonball would fall towards the Earth, but the Earth's surface would curve away beneath it at the exact same rate. It would never land. It would be in orbit. We, all of us, are living on that cannonball. The discovery that the Earth was not a stationary platform but a moving world was one of the most profound revolutions in the history of human thought. Thinkers like Copernicus, Galileo, and Kepler dismantled a worldview that had stood for thousands of years, replacing it with a cosmos in which humanity was not the central focus, but a passenger on a moving vessel. Galileo, facing the Inquisition for his heliocentric views, was forced to recant. But legend has it that as he rose, he muttered under his breath, "Eppur si move." And yet, it moves. He knew that the truth of nature could not be silenced by human decree. The Earth moved, and with that realization, our understanding of stillness was forever shattered. Yet, this is still just our local neighborhood. We have only described the motion of our own planet within its home system. For a long time, we pictured the sun as the grand, stationary anchor at the heart of this celestial clockwork. The planets danced around it, but the sun itself was the master, the motionless hub. This, too, turned out to be another illusion of perspective. Our sun is not an anchor. It is a star, one of hundreds of billions, and it is on a journey of its own, dragging its entire planetary family along for an epic ride through the spiraling arms of the Milky Way galaxy. The scale of this next layer of motion is difficult for the human mind to grasp. Our entire solar system is careening through interstellar space at a velocity of approximately 500,000 miles per hour. That's 483,000 miles per hour, or about 220 kilometers every single second. Even at this blinding speed, the galaxy is so incomprehensibly vast that it takes our sun approximately 230 million years to complete a single orbit around the galactic center. This is what astronomers call a cosmic year. The last time our solar system was in this part of the galaxy, dinosaurs were just beginning to walk the Earth. The next time we pass this way, the continents will be unrecognizable, and the fate of our own species will be long, long since decided. We are travelers through cosmic time as much as through cosmic space. Imagine the Milky Way as a colossal, spinning hurricane of stars, gas, and dust. It is a flattened disk, 100,000 light-years across, with a dense, bright bulge at its center. Within this stellar storm, our solar system is like a tiny speck of dust, located about 2/3 of the way out from the core in a minor spiral arm called the Orion Spur. We are not just orbiting this center, we are also bobbing up and down, passing through the galactic plane like a horse on a cosmic carousel. This oscillation takes tens of millions of years and may have profound effects on our planet. potentially correlating with periods of mass extinction as we pass through denser regions of the galaxy. This grand galactic tour was revealed to us in the early 20th century. Astronomers like Harlow Shapley began to map the distribution of star clusters, realizing that our Sun was not at the center of this stellar system. Then came Edwin Hubble, using the powerful new telescope at Mount Wilson Observatory. He discovered that faint, fuzzy patches in the sky, once called spiral nebulae, were not clouds of gas within our own galaxy as many believed. They were entire galaxies in their own right, island universes as the philosopher Immanuel Kant had speculated, separated from us by millions of light years of empty space. In a single stroke, the known universe expanded by an unimaginable factor. Our Milky Way was not the entirety of creation, but just one galaxy among billions, and if other galaxies existed, it begged the question, were they moving too? The answer turned out to be yes, and in a way that would once again revolutionize our entire conception of reality. Our galaxy, the Milky Way, is not on a solo journey. It is a leading member of a small cluster of about 50 galaxies, known as the Local Group. The other major player in this group is the magnificent Andromeda Galaxy, our closest large galactic neighbor, visible to the naked eye as a faint smudge of light. Andromeda is larger than the Milky Way, a true cosmic heavyweight. And, for billions of years, our two galaxies have been locked in a gravitational dance, pulling inexorably closer to one another. We are not just moving around the galactic center. Our entire galaxy is moving towards Andromeda at a speed of roughly 250,000 miles per hour. We are on a collision course. In approximately 4.5 billion years, what astronomers have dubbed Milkomeda will be born. This will not be a cataclysmic crash in the way we imagine a car wreck. Stars within galaxies are so incredibly far apart that direct collisions will be exceptionally rare. If the Milky Way were the size of North America, the stars would be like individual grains of sand, separated by miles. It is less a collision and more of a merger. Instead, the two galaxies will pass through one another like giant ghosts, but the colossal, combined gravitational fields will wreak havoc on their structures. Great tidal tails of stars and gas will be flung out into intergalactic space. The elegant spiral arms will be torn asunder. The two supermassive black holes, at their respective centers, will begin a long, spiraling dance, eventually merging to form an even more massive black hole at the heart of a new, giant elliptical galaxy. Our solar system will likely be thrown into a new, much larger orbit, far from the newly formed galactic core. The night sky for any future inhabitants of Earth will be transformed into a breathtaking, unfamiliar starscape. This cosmic rendezvous reveals a crucial principle. On every scale, gravity is the great choreographer of motion. It is the force that commands planets to orbit suns, suns to orbit galactic centers, and galaxies to fall toward one another. But the story doesn't even end there. There is another, even more mysterious motion at play. In the 1970s and 80s, astronomers studying the movement of our local group discovered something baffling. After accounting for the motion toward Andromeda, and even the expansion of the universe itself, there was a residual velocity. Our entire galactic neighborhood, a region of space millions of light years across, is being pulled in a specific direction through the cosmos at over 1 million miles per hour. The source of this pull was a mystery. It was dubbed the Great Attractor. It lies some 150 to 250 million light years away, hidden from direct view by the dense dust and stars of our own galactic plane, a region called the Zone of Avoidance. For decades, we knew it was there only by its gravitational influence, a cosmic ghost tugging on our corner of the universe. We now know this region is home to the Laniakea supercluster, a gargantuan collection of over 100,000 galaxies, of which our own local group is just a tiny provincial outpost. We are not just moving within our galaxy or towards Andromeda. Our entire galactic clan is flowing like a river of galaxies towards the densest part of our local supercluster. So, motion is layered upon motion. We spin on a planet which orbits a star. The star orbits a galaxy, which is moving towards a neighboring galaxy, and that entire group of galaxies is being pulled towards an even larger structure. There is no fixed point. There is no stillness. But this raises a deeper question. This explains how times we are moving, but not times why time's motion is so fundamental. To answer that, we must travel back to the very beginning of time itself. The origin of all this cosmic motion can be traced back to a single moment. 13.8 billion years ago, our universe was not born in a state of quiet repose. It erupted into being in an event of unimaginable energy and violence, the Big Bang. In the first fractions of a second, all the space, all the matter, and all the energy that would ever exist was contained in a point of infinite density and temperature. This was not an explosion times in time-space. It was the explosion times of time-space, and it was anything but static. It was a chaotic, turbulent, expanding fireball. Within this primordial soup, tiny quantum fluctuations, minuscule variations in density created swirling eddies and currents. These initial movements, however small, imparted momentum and angular momentum, a tendency to spin to the nascent matter. One of the most fundamental laws of physics is the conservation of angular momentum. It is the same principle a figure skater uses. When she pulls her arms in, her rotational speed increases dramatically because her angular momentum must remain constant. Conversely, if a spinning object breaks apart, the fragments fly off, each carrying a piece of that initial spin with them. This is precisely what happened in the early universe. As the universe expanded and cooled, matter began to clump together under gravity. The slight, initial rotations present in the primordial gas clouds were conserved. As these clouds collapsed to form galaxies and stars, like the skater pulling in her arms, they spun faster and faster. The initial, chaotic motion of the Big Bang was not lost. It was inherited by every structure that would ever form. The spin of our planet, the orbit of our sun, the rotation of our galaxy, all of it is a cosmic inheritance, a distant echo of the universe's violent birth. Nothing is still because the universe was never still to begin with. But there is an even more profound reason for the absence of stillness, one that reshapes our very understanding of space, time, and motion. This insight comes from the mind of Albert Einstein. His theory of special relativity, published in 1905, is built upon a revolutionary idea. All motion is relative. There is no absolute frame of reference, no universal at rest state against which all other movement can be measured. Imagine you are on a perfectly smooth train. With the curtains drawn, you feel no shaking or vibration. You pour a cup of coffee and the liquid sits level. A ball you toss in the air goes straight up and comes straight down. From your perspective, you are completely stationary. Then, you look out the window and see another train on the next track moving past you. But is that train moving, or is yours? Without looking at the ground, at an external reference point, it is impossible to say. Perhaps your train is still and the other is moving forward. Or maybe the other train is still and yours is moving backward. Or perhaps both are moving, but at different speeds. Einstein realized that the laws of physics must be the same for all observers in uniform motion. There is no privileged, stationary observer in the universe. This simple but powerful concept demolishes the classical idea of absolute rest. To be still is a meaningless statement without adding relative to what. You are still relative to the chair you are sitting on. You are moving at 1,000 miles per hour relative to the center of the Earth. You are moving at 67,000 miles per hour relative to the Sunday. You are moving at 500,000 miles per hour relative to the galactic center. There is no master coordinate system, no cosmic origin point where we can say, here, this is the place of true and final rest. Motion is simply a description of the relationship between objects. Einstein's general theory of relativity took this a step further. He revealed that gravity is not a force in the Newtonian sense, but rather a consequence of the curvature of a four-dimensional fabric called spacetime. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells mass and energy how to move. A planet orbiting the Sun is not being pulled by an invisible rope. The Sun's immense mass creates a deep depression, a gravity well, in the fabric of space-time. The planet is simply following the straightest possible path, a geodesic, through this curved geometry. In a sense, the planet thinks it is traveling in a straight line. It is the shape of space itself that bends its path into an orbit. So, orbital motion is not a struggle against a force. It is the natural, effortless consequence of existing within a universe warped by mass. From the conservation of primordial momentum to the relativity of spacetime, the reasons for perpetual motion in the large-scale universe are profound. But the ultimate prohibition against stillness lies not in the vastness of the cosmos, but in the impossibly small and bizarre world of the quantum realm. Here, at the fundamental level of reality, the very concept of a particle being perfectly still is not just unlikely, it is forbidden by the laws of nature. The governing principle of this subatomic world is the Heisenberg Uncertainty Principle. Formulated by Werner Heisenberg in 1927, it stands as one of the cornerstones of modern physics. It states that there is a fundamental limit to the precision with which we can know certain pairs of physical properties of a particle simultaneously. The most famous of these pairs is position and momentum. The more precisely you know where a particle is, the less precisely you can know its momentum, which includes its velocity, and vice versa. This is not a limitation of our measuring instruments. It is not that we are clumsy, it is an intrinsic, baked-in feature of the universe. To understand why, think about how we see something. To see an object, photons of light must bounce off it and enter our eyes. For a large object like a baseball, the impact of these photons has a negligible effect. But for a tiny particle like an electron, the act of observation is a violent event. To pinpoint its position with high accuracy, you need to hit it with a high-energy photon, one with a very short wavelength. But that very act of hitting it with a high-energy photon imparts a significant and unpredictable amount of momentum, changing its velocity. The more you try to pin down its location, the more you disturb its motion. Now, consider what it would mean for a particle to be truly still. Still means its velocity, and therefore its momentum, is exactly zero. If you knew its momentum was precisely zero, the uncertainty principle dictates that your knowledge of its position would have to be infinitely uncertain. The particle would have to be everywhere in the universe at once. Conversely, if you knew its position was exactly here, right at this one point, its momentum would be completely unknown. It could be moving at any speed, in any direction. A particle cannot have both a definite position and a definite momentum of zero. Therefore, a particle can never, ever be perfectly still. This fundamental restlessness of the quantum world gives rise to a startling phenomenon: zero-point energy. Even if you could cool a system down to absolute zero, the theoretical temperature at which all thermal motion ceases, the particles within that system would not become stationary. They would still retain a minimum, teen amount of vibrational energy, a residual quantum jiggle. The vacuum of empty space is not truly empty. It is a roiling sea of virtual particles, popping in and out of existence, a quantum foam of energy. The universe, even in its coldest, emptiest state, hums with a baseline energy that makes true stasis an absolute impossibility. The very fabric of reality is restless. This brings us to the most philosophical implication of universal motion. It is inextricably linked to the very flow of time itself. The second law of thermodynamics, one of the most robust principles in all of science, states that the total entropy, or disorder, of a closed system will always increase over time. Things fall apart. A hot cup of coffee cools down as its heat energy dissipates into the room. A neat stack of papers tends to become scattered. This relentless march toward disorder is what gives time its arrow, its forward direction. Motion is the primary mechanism for this process. Particles in motion collide, transferring energy and spreading it out. Stars burn through their fuel, radiating light and heat across the cosmos. Galaxies merge, randomizing the orbits of their stellar populations. This constant change, this ceaseless activity on every scale, is the engine of entropy. It is what separates the past from the future. A universe that was truly still would be a universe in a state of perfect equilibrium. There would be no change, no processes, no events. In such a universe, time would have no meaning. The ceaseless motion of the cosmos is, in a very real sense, the ticking of the cosmic clock. And the grandest motion of all, the one that defines the ultimate fate of the universe, is the expansion of space itself. When Edwin Hubble observed distant galaxies, he noticed their light was shifted toward the red end of the spectrum. This redshift is a cosmic Doppler effect, indicating that these galaxies are moving away from us. And the farther away a galaxy is, the faster it appears to be receding. This observation was the first proof that our universe is expanding. The best analogy is that of raisins in a loaf of baking bread. As the dough rises, it carries all the raisins along with it. From the perspective of any single raisin, all the other raisins seem to be moving away from it. The raisins aren't moving times through times the dough. The space between them, the dough itself, is expanding. This is the ultimate motion. It is not the movement of objects through space, but the very stretching of the fabric of space-time, carrying all the galaxies along for the ride. This expansion, which has been accelerating for the last few billion years due to a mysterious force we call dark energy, is the final and most profound expression of the universe's dynamic nature. So where is all this motion leading? The current cosmological model points towards a future known as the heat death of the universe. Trillions of years from now, all the stars will have burned out. The galaxies will be populated by cold, dead remnants like black dwarfs, neutron stars, and black holes. The universe will continue to expand, becoming ever colder, emptier, and darker. Eventually, even the supermassive black holes will evaporate through Hawking radiation, over timescales so vast they defy human language. In this distant, desolate future, the universe will approach a state of maximum entropy. All energy will be distributed perfectly evenly. All temperature differences will vanish. All organized structures will have decayed. In this state of near-perfect equilibrium, meaningful directed motion will cease. All that will remain is the faint, random quantum jiggle of zero-point energy in an endless, cold, dark void. This may be the closest the universe can ever get to stillness. Not a state of peaceful rest, but the stillness of absolute death. We return then to our starting point, to the illusion of the still mountain. We now see it not as a static object, but as a dynamic process, a temporary collection of buzzing atoms, participating in a planetary spin, an orbital journey, a galactic waltz, and a cosmic expansion. Its apparent stillness is just a fleeting moment of stability in its own frame of reference, a momentary pause in a story of ceaseless transformation. The universe's refusal to stand still is not a flaw or a curiosity. It is the very essence of its being. It is the signature of energy, the expression of time, the consequence of its own explosive birth. To be is to move. To exist is to change. The cosmos is not a static portrait, but an epic, unfolding narrative written in the language of motion. And we, on our spinning, orbiting, speeding planet, are not merely observers of this grand spectacle. We are a part of it. We are composed of the same restless stardust, governed by the same laws of motion, and carried along on the same incredible cosmic journey. In the universal dance of existence, there are no spectators. There is only the music and the motion